To finish our survey of the structures of extended solids, we're going to look at three more structures. Two of them are ternary structures, seen mostly for oxides, and one a quaternary structure. And these structures house families of compounds which have many important functional properties. We're going to start with the Spinel structure, which takes its name from the mineral spinel, magnesium aluminum 2O4. The structure of Spinel is shown here on the left. I'll say a little bit more about it on the following slides. Fe3O4, the mineral magnetite, is the oldest known magnetic material. The Chinese used magnetite to make compasses over 2,000 years ago, and Spinels still find many applications for their magnetic properties. In the Spinel structure, the magnesium goes onto a tetrahedral site, and the aluminum goes onto an octahedral site. In the table we see here at the bottom, we've listed just a handful of spinels, each of them representing a different oxidation state on the tetrahedral and octahedral sites. So you can see on the tetrahedral sites, we can go all the way from a 1+ cation like lithium, all the way down to a 6+ cation like tungsten. And then the octahedral sites, their charges vary depending on the charge on the tetrahedral site. Let's take a closer look at the structure of Spinel. In some ways, it's a kind of complicated structure. You can see from the Wyckoff positions in the table below that there are 56 atoms in the unit cell. The most common way to describe Spinel would be to start with a cubic close-packed array of oxygens, and then fill up 1/2 of the octahedral holes with aluminum, and then 1/8 of the tetrahedral holes with magnesium. If we dig a little deeper, we could look at the frameworks that we get just from the tetrahedra or just from the octahedra. So on the left, I've removed the aluminum, so the only thing we see are the magnesium and the oxygen. And in that view, what you can see is the magnesium-centered tetrahedra are not connected to each other. All right, they're isolated from each other. And if we looked a little bit closer, we would see that those tetrahedra occupy the exact same positions that the carbon atoms in the diamond structure occupy. And the space group, FD3 bar M, is the same for both diamond and Spinel. If we look on the right at the aluminum oxide framework, there I've removed the magnesium cations. You can see that the aluminum octahedra share edges, and those edges make chains that run in a variety of directions. Maybe the fact that we see edge-sharing octahedra isn't too surprising. Remember that if we filled all of the octahedral holes, we would have the rock salt structure, which would have all of its edges shared. In Spinel, not all of the edges of each octahedron are shared, but we still get this network of edge-sharing octahedra. You can see from the site symmetries, 4 bar 3M, that is the perfect symmetry for a tetrahedron, so the magnesium atom anyway is on a site that has perfect tetrahedral symmetry. We could draw a bond graph for the Spinel structure, which I've done here. And so in this bond graph, you can see that we do obey Pauling's rule of parsimony. Of course, we knew that must be the case from the Wyckoff sites on the previous slide, because all of the oxygens are on a single Wyckoff site, so therefore they're all crystallographically and chemically equivalent. And we can say the same for magnesium and aluminum. You can see here that the oxygen makes 1 bond to magnesium and then 3 bonds to aluminum. So we could write the crystal chemical formula in this way. Magnesium's coordination number is 4, aluminum's coordination number is 6, and then the oxygen has 4 neighbors, 1 magnesium and 3 aluminums. The mineral spinel, like many other spinels, is what we call a normal spinel structure. And what we mean by that is we have, 1 magnesium and 2 aluminums. So the element that's present in the smaller amount, only one of them, magnesium, goes onto the tetrahedral side. And then the other cation, of which there are two per formula unit, occupies the octahedral sites. But oftentimes we'll find what are called inverse spinels. And in an inverse spinel, like TiFe2O4, the cation that's in the minority, here the titanium, has a preference to go onto the octahedral site. And so that means the other cation, which is present in the majority, are split between the octahedral and tetrahedral sites. So in an inverse spinel, we have a disordered or random distribution of two different cations on the octahedral sites. The next structure I'd like to introduce you to is called the garnet structure. One example of a garnet is this magnesium 3, aluminum 2, silicon 3, O12. If you thought spinel was a complicated structure, this structure is even more complicated. We'll say a little bit more about the structure on the next slide. Key takeaway point here is that some of the cations, here the magnesium, are in a coordination which is basically a distorted cube. Other cations, here the aluminum, are in an octahedron, and the smallest cations, typically, here the silicon, go on to tetrahedral sites. Garnets also find important technological applications. If you take a garnet that's called YAG, yttrium 3, aluminum 5, O12, so in that case, aluminum occupies both the tetrahedral and the octahedral sites, and then we dope in a small amount of neodymium for yttrium, we get what is arguably the most important laser crystal known. Neodymium doped YAG emits infrared light with a wavelength of 1064 nanometers. If you frequency double that, then you get green light of 532 nanometers. So you're probably familiar with this from a green laser pointer, but it's also used in mini lasers. If we replace the aluminum with iron, yttrium iron garnet, then we get a material that's called YIG, which is a really important magnetic material. So a lot of garnets are important for their magnetism. And then it's also worth pointing out that if you have garnets where the octahedral sites are aluminum and some of that aluminum is replaced with chromium, you can get precious gemstones that have colors that are in fact very close to that of ruby. The picture we see here is something called the Black Prince's ruby, which is a famous ruby from history. And it's not a ruby at all, it's a garnet. So some of the most important rubies are actually garnets. There's a whole family of garnets you can get depending on what ions you put on the cubic sites, the octahedral sites, and the tetrahedral sites. If we were to look just a little bit more carefully at the structure, here's the details for magnesium aluminum silicate. The space group is IA3'D. That is space group number 230. So that is the very last space group, and you might argue the most symmetric space group in the international tables. There are now 160 atoms in the unit cell, but amazingly, each atom goes onto a single Wyckoff site. So that means that all of the silicons are crystallographically and chemically equivalent. And we can say the same for aluminum, for magnesium, and for oxygen. So once again, here we obey Pauling's rule of parsimony. The bond graph is a bit complicated to draw because there's so many different atoms, but we can just write the crystal chemical formula, which is shown here. So the magnesium is 8-coordinate, the aluminum 6-coordinate, the silicon 4-coordinate, and then the oxygen, we see once again has 4 bonds to the cations. 2 bonds to magnesium, 1 to silicon, and 1 to aluminum. The last structure I want to talk about might be the most important of all, and this is the perovskite structure. The perovskite structure is much simpler than spinel or garnet. And in fact, in the perovskite structure, we only have 5 atoms in the unit cell. We have a small cation, here titanium, which sits at the origin on the corners of the cubic unit cell. We have an oxygen, it goes at the middle of each edge of the unit cell. And then we have a larger cation, here's strontium, which goes in the body center of the unit cell. If we were to take the strontium away and expand the structure out, you would see that the structure contains titanium-centered octahedra with each oxygen bridging to another octahedron. So we have an infinite network of corner-connected octahedra. That is exactly the same thing as the rhenium trioxide structure. So you might think about this as being a stuffed rhenium trioxide compound. The strontium sits here in the middle. Well, there's a cavity in the middle of that framework of corner-connected octahedra. And the coordination environment of the strontium is a cube octahedron. That is to say, it has 12 nearest neighbors. That's how many edges there are for a cube. So the crystal chemical formula is strontium 12 coordinate, titanium 6 coordinate, and then the oxygen has 4 strontiums around it and 2 titaniums. Here would be another view of the coordination environments of the 3 ions in the perovskite structure. An important consideration when we're thinking about the perovskite structure has to do with the sizes of the ions that we put into the structure. To define the perovskite structure, we only have one variable, and that would be the length of the cubic cell edge. Yet, we're trying to meet 2 criteria. We're trying to get the optimal titanium oxide distance, while at the same time getting the optimal strontium oxide distance. And we can evaluate how well we satisfy the bonding requirements of both ions with something called the tolerance factor. So this was developed by a Norwegian chemist about 100 years ago, a guy named Victor Goldschmidt, who was one of the first people to make synthetic perovskites in the lab. I didn't say so earlier, but the name perovskite comes from the mineral calcium titanium 03. All right, so what is the tolerance factor? Well, let's take a look at this crystal structure. Here I've drawn the crystal structure with the ions at a realistic space-filling radius. This actually brings me to another way we can describe the perovskite structure. If we were to think about the oxygens and the strontiums as forming a cubic close pack arrangement, right? So think about cubic close packing strontium 03 layers. And then if you looked in those layers, only some of the octahedral holes are not next to a strontium. They're only surrounded by oxygen. If we filled up all of those holes that have only oxygen neighbors with titanium, we would get the perovskite structure. That's how we can view this structure when we think about the ions at their true size. Now, how do we define the edge length, the size of the unit cell? Well, if we were to take away a cut from the top of the unit cell here and look at it, you can see that the titanium and oxygen touch along the cell edge. Okay? If we were to take a cut right out of the middle of the unit cell, in that one, the strontium and the oxygen touch along this face diagonal. Okay, now if we look at the length of the edge of the cubic unit cell, we could define it either in terms of the titanium and oxygen radius or in terms of the strontium and the oxygen radius. If we were to define it in terms of the smaller octahedral cation, you see we have one radius of the small cation, two radii of the anion, and then one more radius of the small cation. So we call that small cation B. That's often done. We can say that unit cell edge length is twice the radius of B plus the radius of the anion X. Now, if we go to the lower drawing, there the ions are touching along the face diagonal. So the distance along the face diagonal is going to be twice the radius of A plus the radius of the anion X. This is a 45-degree right triangle. So if the hypotenuse is 2 times the radius of A plus the radius of X, then the edge is going to be that value divided by the square root of 2. Now we can simplify that to get this. Okay, so now we have two expressions for what the unit cell edge should be, and we can use those to calculate the tolerance factor. So Goldschmidt's idea was to say the tolerance factor is the unit cell that's optimal for the larger A cation, that's the numerator, divided by the unit cell parameter, A, that's optimal for the smaller octahedral cation, B. We can, once again, simplify this equation just a little bit, and we're just left with the square root of 2 in the denominator. Now, if we choose just the right cations, so the numerator and the denominator are equal, that means everything fits together just right, then the tolerance factor would be 1. That, we would say, is a perfect fit. If the tolerance factor is larger than 1, it means the A cation is too big. It's stretching that framework of corner-connected octahedra to fit in. If the tolerance factor is less than 1, it means the A cation is actually too small for the framework. It kind of rattles around in that framework of corner-connected octahedra. All right, now let's look at just a few selected compositions and their tolerance factors. Strontium titanate, as it turns out, is a perfect fit, basically. The tolerance factor to 3 significant figures is 1. But if I replace the strontium with barium, which is larger, now the tolerance factor gets larger than 1. And if I then replace the titanium with the manganese, which is smaller, manganese 4, then I'll get an even larger tolerance factor. I could go in the other direction by replacing the strontium with the calcium, which is smaller, and I can see tolerance factors that are then, less than 1. And if I replace the calcium with magnesium, the tolerance factor drops down to about 0.85. The magnesium titanate and the barium manganate here at the top and the bottom are not actually perovskites, so they don't maintain this perfect corner-connected environment. The compounds shown in green maintain the framework of the perovskite, but they are distorted in ways I'm about to describe. So let's first talk about what happens when the tolerance factor is too large. For barium titanate, what happens is the tolerance factor is a little bit bigger than 1, and so that effectively stretches the octahedron out, and because of that, the titanium can shift off center of the octahedron. All right, this creates a local dipole moment, and that's really important. This kind of distortion for ferroelectric materials, barium titanate is an archetypal ferroelectric material. It's also important for piezoelectric materials, and so many dielectric materials are based on these perovskites with a tolerance factor just a little bit larger than 1. In barium manganate, the tolerance factor is larger still, and now, in fact, it's just too big to keep that corner-connected framework. So we go to something which is called a hexagonal perovskite, but which has a very different connectivity. And now I'll say a little bit more about those so-called hexagonal perovskites. So the hexagonal, or sometimes these are rhombohedral perovskites, what happens is, remember that I was telling you we can think about perovskite as cubic close packing of AX3 layers or AO3 layers. Well, if we have some mixture of cubic and hexagonal close packing of these layers, we can get a different connectivity of the octahedra. If we had all hexagonal packing of barium and oxygen layers, then we would end up with what's called the 2H structure. So this has a hexagonal space group, and it's 2 layers before it repeats. And in this structure, the octahedra don't share corners, they share faces. Infinite chains of face-sharing octahedra. And because the chains aren't connected, they can move farther apart, and that allows enough room for the barium to fit in between these chains. Then there are these other structures which actually have a mixture of cubic and hexagonal close packing. And because of that, we can get both corner-connected octahedra and face-sharing octahedra. So in the 4H structure, there's 4 layers before it repeats, and we get dimers of phase-sharing octahedra that share corners. In the 9R structure, we actually have 9 layers before the structure repeats. This is a rhombohedral space group, and this one has trimers of phase-sharing octahedra that are connected by corners to other trimers. And then here we have the 6H structure, which is seen for barium titanate under high pressures. And in that one, you have both dimers of phase-sharing octahedra. You have some sites which are only connected by corners to other octahedra, and then more dimers. All right, so these are some of the hexagonal perovskites, and we expect to see these when the tolerance factor gets larger than 1. What happens when the tolerance factor gets smaller than 1? In that case, it's like the large A cation is sort of rattling around, right? It's not close enough to touch all of its neighbors. So what happens then is we get a distortion that's called an octahedral tilting distortion. So the octahedra tilt in a manner that I've shown here. So we keep effectively something that's very close to an octahedral environment around our small cation, say around our titanium. But we distort the environment around the larger calcium here in a pretty substantial way. Some of the oxygens move closer to it, others move farther away. That effectively reduces its coordination number from 12 down to something that's probably better described as 8. Now, if we were to continue to decrease the tolerance factor far enough, at some point, the perovskite structure, even a distorted perovskite structure, is not going to be stable. And usually, the structure that emerges when we get tolerance factors too small is the Ilmanite structure, which I show here for magnesium titanium O3. You can think of the Ilmanite structure as corundum, the aluminum oxide structure. And remember, in corundum, there are pairs of phase-sharing octahedra. But in Ilmanite, those octahedra are ordered. On one octahedron, we have a titanium, and on the other, we have a magnesium. So we have magnesium layers, titanium layers. Probably most importantly here, the coordination number of the alkaline earth cation now has gone down to 6, right, which is a more reasonable coordination for a smaller alkaline earth like magnesium. Bottom line is there are many perovskites, literally thousands of perovskites. There are quite a few cubic ones, but in fact there's even a much higher proportion of ones that are distorted in manners like we see here for calcium titanate. And then we have others that are distorted like barium titanate. So it's a very rich family of compounds, and we'll see it time and time again when we start talking about properties.